Okay, Chapter 14 is about oscillatory motion, specifically simple harmonic motion, and we'll give meaning to what we mean by simple and simple harmonic motion as we go along. But for right now, let's just focus on oscillatory motion, and this is motion we've actually seen because of Hooke's law and the spring equation, the spring force equation. We see that a spring is a restoring force that takes a mass that is pulled some position away from x equals 0. So here we have x equals 0. When we pull the mass to the right, some positive position, our negative in Hooke's law turns around the force, makes the acceleration negative, and wants to pull it back to 0. If we look down on the page a little further, if we push the spring and get x equals a negative value, then what we see is the Hooke's law. The negative now turns it around and makes it a positive. So again, the force pushes back into the neutral position. So any force, and that's why I have down here, any linear force with a negative slope is simple harmonic motion. That's a feature that as soon as you see a negative linear slope on a force, you should be thinking, oh, I'm in a region of simple harmonic motion. And there are a couple of systems that display this behavior, not just the spring and the mass. One of the systems we're going to study is called the simple pendulum. The displacement is now based on a displacement theta from an x equals 0, and it's gravity that pulls the mass back to position 0. But it's not just mg, it's only the mg sine theta component that pulls it back to 0. So technically, we don't have a force that is linear with position with a negative slope. We have a force that is negative, pulling it back to 0 when we displace it to the right, if we want to say that's a positive arc length distance. But it's sine theta, not theta. So if we could scribble out sine theta and just make it theta, then we would have a situation identical to Hooke's law. And it turns out that's what we're going to end up with, to a very good approximation when we look at only displacing the pendulum a very little amount. In fact, sine theta doesn't just approximate theta when theta equals 0. When theta equals 0, sine of 0 is 0, so we have a perfect situation. So if we go off of 0 from 1, 2, 3, up to about 10 degrees, we get to a very good approximation, have that the force pulling that pendulum back to 0 is given by negative mg sine theta, where the mg plays the same role as that spring constant. Now, to remind you what the role of that spring constant is, the spring constant in Hooke's law was given by newtons per meter, force in newtons, position in meters. So really that described the strength of the spring. How many newtons does it take per meter to stretch that spring? So the larger the K value, the stronger the spring. So it's a strength parameter. We're going to see that mg is also a strength parameter, and the larger the mg value, the stronger the pull back to 0. And that will determine how quickly the pendulum goes back and forth, or our spring constant, how quickly the mass goes back and forth. Okay, now for a more detailed mathematical analysis, we're going to look at considering what would happen if we took actual data. So I want you to think of these data points, this M, this M, this M, as coming from an actual strobe photograph or position versus time data that is taken when a mass is pulled to the right, some amount, positive x, released from rest. So we're saying we're beginning our analysis window at time t equals 0, when the x position is at a max value, and if you remember from what we did with Hooke's law, that would be the amplitude of that oscillation. So when we release the mass, it picks up speed, and then picks up more speed, and then has maximum speed right at position x equals 0, after which it begins to slow down a little more, and then finally comes to a stop here at position negative A. So let me clean this up a little bit. I want you to consider this pink graph, or pink data, to be actual data. So it's an experimental result, an empirical equation, that if we flipped it on its side, if I rotated it this way, I could make it into a perfect cosine function, and that's exactly what I have on the bottom of the page here. So x equals a cosine omega t plus phi is going to be the equation we use for all simple harmonic motion, and we'll vary the parameters a little bit, whether it's a spring or whether it's a pendulum. But to remind you of your trigonometry, the bracketed term represents the total angle that goes with the cosine, and the phi value is called the phase shift, which is the shift of the phase. So the whole thing together is the phase, and the phi is the shift of the phase. And the phase shift is really nothing more than the initial angle that the block is at when we start our stopwatch and begin our analysis window. So at time t equals 0, if there's a phase shift value in there, that would be where we begin our analysis. And more on that in another page or two of notes. The other thing that absolutely appears that may seem out of the ordinary is this radian per second omega term, because it's a circular motion term. So omega was the radians per second in angle that represented the angular velocity of a particle. And if you notice, we don't have any angular motion here. We only have linear motion back and forth. So just as it says CE page 13, we're going to jump ahead to page 13, our appendix, and see why it is that it definitely makes sense to utilize that radian per second value. And here we have it. So we have our x equals a cosine omega t, and notice there's no phase angle in here. So at time t equals 0, cosine of 0 is positive 1, so x is at positive a, and we have a little different perspective here, because if I take this to represent the x equals 0 mark, then to set this in motion in the same sense that we've been talking about, down is actually going to be the positive a that we had in our side-to-side motion. So we're going to pull it down. We're going to let that correspond to theta equals 0, when little t equals 0, and we let it go, and it's going to oscillate between positive a and negative a is actually going to be up here, and it's going to oscillate back and forth. Well, that circular motion that we were talking about is not just a theoretical, mathematical mapping of a rotational variable into a linear variable. It's an actual projection, right? The shadow of the peg of a wheel spinning matching the linear motion, so that the omega we're talking about is an omega that literally one-to-one maps onto the linear motion of the spring up and down. I always thought that was kind of cool. And it is not just some math theory. It actually matches up, that if we were talented enough, we could take that peg, start it down here, and have the shadow match exactly the center of the mass as the mass goes up and down. So that at 90 degrees, the block has gone through 1/4 of its motion, half the motion up to negative a, 3/4 of the motion back down, and the omega will match perfectly. Okay, let's go back to page 3. Yes, page 3. Okay, so on this page, we're taking x equals a cosine omega t plus phi as an empirical result. So you don't have to prove it. That is going to be one of the equations we'll need to memorize for simple harmonic motion. You don't want to have to look that up. The position in all simple harmonic motion is given by a cosine omega t plus phi. Well, if we need the velocity function, we don't need anybody to give that to us. We can just take the derivative of that position function, and we will get our velocity function. Now, we have to be a little bit careful, because we need to take the derivative of cosine theta, which is negative sine theta d theta dt. So this you do not need to memorize. Those of you that are in calculus, I hope, recognize it right away. But if not, it is on the AP equation sheet, so the derivative we can easily take by knowing that it's negative sine theta d theta dt. And please note that that d theta dt is very important because that brings an omega outside. The omega a represents the amplitude of the sine function, and since it's a velocity function we're plotting, that's the maximum velocity for our oscillation, which of course we know occurs 1/4 of the way in. And then it will also occur 3/4 of the way in when it's going back to where it started. So the functions absolutely make sense. If we want the acceleration acceleration function, we simply take dv dt equals the acceleration, and that's exactly what we've done here. And again, we're taking derivative of sine, so we get positive this time cosine d theta dt, and that pulls out another omega for us, so we get omega squared a is the amplitude of our function, which now is an acceleration function, and we get the acceleration max equals omega squared a. Notice what else we get here. This is interesting. If you look closely at the acceleration function, we get an a cosine omega t plus phi, and that's exactly what we have up here. X equals a cosine omega t plus phi. So we can replace that with an x, and look at what we get. We get the acceleration as a function of time equals negative omega squared x. And this, if we think about it, should not be a surprise at all, because the block on the spring is given by Hooke's law, F equals minus kx, Newton's second law, equals ma. So look at that. X and a go together in a very linear way, and look, x and a go together. If we double x, we double a. So there you have it. That is our first lecture notes for chapter 14, and we are on our way.